Understanding Science, this UNDSCI webpage of University of California, Berkeley campus is a good link. And there are several links that you can move to by using their next button on every page. And then there is a serious encyclopedia on philosophy of science at plato.stanford.edu. That's a Stanford University website. Okay, so as I said, before I begin this, let me show you a little clip of, um, actually I do want to keep sharing, but what I want to do is I want to, yeah, so I want to, yeah, now it's fine. Yeah, let me show you a little film that tells you about the power of science. Okay, in fact, most of us are literally awed by science, right? We, right from childhood, we are told again and again that we live in an age of science, which sometimes actually I doubt, because most decisions we make in our lives are, are not really scientific in nature. They're mostly dictated by other institutions like religion or tradition, or etc. Anyway, so but let's look at the power of science. So this is one way of looking at it. So what this film does is it shows you how you, as you go from a more a kind of length scale that we are familiar with, say a meter square, okay, to larger length scales. And so every 10 seconds, you'll be going to a 10 times larger length scale until you go to whatever was the visible horizon for the universe at the time when the film was made. The film was made by a couple, Philip and Phyllis Morrison, and it was originally printed as a book, and then the film was made 25 years ago. There are several versions of it available, so let's look at it.
The picnic near the lakeside in Chicago is the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1 million meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This squares 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. Ten to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the two inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus. So massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks in intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
Okay, so yeah, so that was a film just to remind ourselves what is scientific knowledge. You can look at nature in many different ways. Length scale is one way of looking at it. Another could be time scale. You know, there are processes happening extremely fast beyond our imagination. Uh, Today, any average physics or chemistry researcher is trying to understand processes that are happening at a scale which is like faster than trillion times in a second. Okay, so a trillion is what, 10 to the power 12, so much faster than that, 1,000 times faster than that. uh, on the other hand, you can also think of time scale which is much slower, so things that happen over millions of years, like for instance what the paleobotanists look at, when they study fossils, and or when people are looking at cosmology, what has happened over zillions of years. Um Also, you can look at energy scale, for instance, things that have that involve very small amount of energy, weak interactions in subnuclear particles, or things that involve huge amounts of energy, like for instance the nuclear explosions, and explosions that are happening in the stars and things like that. So there are many different ways of looking at nature. Scales of quantities is one thing. Another is the forms that natural systems have. You have, uh, astronomical forms. You just saw the galaxies and these, clusters and superclusters. You can look at forms on Earth, the geological forms, or you can look at forms in biological systems, the cellular forms, and or eventually the molecular structure. So form is another way of looking at natural systems. So in all this, we are basically trying to acquire information about nature, right? And that's what, when we think that this is the truth, that is what nature is like, we say that we have some knowledge about nature. But knowledge itself is a fairly complicated idea. And this is a cartoon that demonstrates that. Depending on how you're looking at an object, you may actually reach a different conclusion. So how do we actually acquire knowledge? The primary means of acquiring knowledge are common sense, uh, language, perception, reason, emotion, and none of these is foolproof. Common sense, of course, it's called common because we think all of us have that kind of sense, but indeed common sense is, it can vary from person to person, depending on whether you are a forest dweller or an modern urban dweller, depending on whether you have gone to school or not. Sometimes it also depends on who you are, whether you are a man or a woman, what kind of culture or tradition you have come from. So it's not really that common. Okay. So anyway, I'm sure nobody would argue that common sense cannot lead us to an absolute understanding, or absolute truth. Now, language is, of course, a very important means of acquiring knowledge. Everything we do has some language. I mean, we think in a language. So today is of course not the time to get into details, but there have been huge debates on how we acquire knowledge using language. And it is generally believed now that language is fundamentally important on how we develop a knowledge base, right? And that's why mother tongue education is so important. But anyway, that's another debate, and so let's not get into that. But what should be clear to you is that language can be used and abused. I mean, we can learn the right things using a language, or we can learn the wrong things, or there can be many rights. Okay, so a humanist who does not believe in nationalist boundaries has their own way of reading books and acquiring knowledge. Nationalists have their own ways of reading books and acquiring knowledge. Religious texts give one kind of knowledge to the believer. To the non-believer, it is merely a text which is worth reading because it is rich in literature or traditional knowledge and etc. So in other words, there's it's not a foolproof way of acquiring knowledge. Okay, it can give you multiple kinds of knowledge. And so if you're looking for knowledge as truth, well, it's a problem. Perception, well, this cartoon tells you very well. There are many such millions of cartoons available on the internet to tell you about optical illusion. So that's just using one sense, which is our eyes. Uh, but even other senses like touch and smell and etc. can lead to different kinds of understanding about whatever we are trying to study. Then we think that, well, of course, there are problems with language and perception, but we can reason, right? But reasoning again, is not really as foolproof as we would normally like to think, because uh, every particular kind of background gives rise to its own kind of reasoning. And so normally in philosophy, people talk about what is called syllogisms. So you have a logical structure for reasoning. You're given some premises and you develop arguments, and then you have some inference. So for instance, you see crows which are black, and you see buffaloes which are black, and you see crows that fly. So you argue that black objects can fly, and you infer that buffaloes should be able to fly. So, depending on the way we develop a logical structure of reasoning, we can reach an inference which may or may not be correct. It is possible that the premises are right and the arguments are right, and then, of course, it's very difficult to reach a wrong inference. But it's quite possible that you reach the right inference not using the right kind of arguments. Or I mean, anything could be wrong, premises could be wrong, arguments could be wrong. Okay, so the validity of the truth does not necessarily have much to do with the validity of the premises and the arguments. Emotion is something that most of us think cannot be a way of acquiring knowledge. I mean, we always say don't be sentimental, right? And it's only in last half century that philosophers have started believing that emotion can be a powerful way of acquiring knowledge. And so unless somebody asks me questions on this, I will not dwell on it, but it's an interesting area to think about. Okay. um, all right, so here is a simple example of telling you how knowledge can be a problem. So we are all used to the map on the left from our middle school geography education. It's a political map of the world. And well, you know what it is. It's a two-dimensional projection of a three-dimensional world, right? You have a near spherical Earth, and you're projecting it on a screen here or on paper when you look at a print. And in the process, if you cut a sphere like an apple or a ball, okay, if you cut it out and spread it on a screen, you will have to stretch some parts and shrink some parts, right? So in the process, what happens is some areas are exaggerated and some other areas are understated. And in other words, if you take a square centimeter from any given part of the map, they do not necessarily represent the same landmass. Okay. And so obviously, you can decide what to exaggerate and what not to. So because the modern cartography has come to us from Europe, so Europeans put themselves at the center of the map, And so this is Europe. So if you look at the non-Russian part of Europe, that's almost that's actually bigger than India. So this is Europe and this is India, and Africa is this continent. And look, Africa is almost like Greenland. But if you have another way of looking at, so this is called Mercator projection. If you have another way of looking at the world map, which is called the Hobo-Dyer representation, where the equal areas on the map, say 1 square centimeter here or 1 square centimeter here, they represent this equal landmass. Meaning, I mean, let's not talk about the roughness of topology. Like, we are not talking about hills and valleys, but otherwise the surface area is the same, right? Then look at what happens to the map. Now look at Africa and look at Greenland, okay? And look at India and look at Europe, okay? So India has almost the same area as the non-Russian part of Europe, okay? That is excluding Russia, whatever is Europe. So in other words, it's literally what you can call Eurocentrism, in this kind of a cartography. Okay, so depending on how you draw a map, you emphasize certain ideas, certain things. Then also there's this question of what is down and what is up. Okay, who decides that some countries are up in the map and some are down in the map? Okay, so this choice we have made of calling a particular direction north and then indicating that as up is actually an ideological choice, because up and down are quite value loaded words. So we always say God stays up there and down there are demons, right? So anyway, so that's just a simple example to tell you how knowledge that we derive is uh, it's a problematic. It's not so clearly the truth. So here is a interesting depiction of this problem by a Belgian artist from 100 years ago. And so this particular thing, which is a smoking pipe, usually people put tobacco here, then light it up and then smoke it, right? That's the pipe. And in French, it says here that this is not a pipe. So what is it then? Right? So you can be a poet and try to imagine what it is, maybe some kind of a fancy pen or umbrella stick or hockey stick or something. Well, the answer is that it's a picture of a pipe. Okay, so the point is that what we see is not the actual reality. Okay, so here is a slogan that Lagemart's book has, or otherwise also philosophers have used it earlier. It says the map is not the territory. So the same thing will be true when we look at anything in nature. So you go to a window and lift the screen, and you take a couple of your students there, ask them to note down 5 things in 1 minute, and you'll be surprised how different those 5 things would be. I mean, as long as you don't give them too much time, and you'll see that it's the same visuals scenario out there, but they all see different things, and it can often depend on who they are, again, men or women, and etc. Okay, so this particular picture was called Betrayal of Images. It's by René Magritte, a Belgian surrealist. Okay, so it's because of this problem with knowledge, we often fall into what is called intellectual fallacies. uh, we are right from our childhood, when we are born, of course we are born as natural explorers. We try to find out things all around us. We learn language, we learn all kinds of habits, and then we practice exploration. And but as we grow, we are constantly told that certain uh, ideas are are to be respected, and we must believe in certain things. And at some point in our lives, we often find out that some of the beliefs that we have from our childhood are not necessarily correct. And it's a painful realization. It's a painful realization. I can give you many examples. For instance, one such example would be that it's a painful realization to know that we are not necessarily the best in the world. Okay, right from childhood, we are often told that we are the best. We are just like anybody else. Nobody is better than us, nobody is worse than us. Now this sometimes is a difficult realization. So this cartoon shows you that you have this one counter where you have comforting lies, and the other counter where you have unpleasant truths. Everybody wants to go for comforting lies. Nobody wants to suffer from the realization that a truth is painful. So normally we say seeing is believing, but instead what usually happens is, we end up seeing things as we believe in them. And even in history of science, there are many such examples. For instance, in the 19th century, sometime after 1860s, telescopes were fairly advanced by then, but still they were not that great. And people were still trying to understand little deviations in the trajectories of planets moving around the sun from the calculations they made using the theory of gravitation. And so there were speculations about new planets, for instance, Pluto and Uranus, etc. uh, their existence was necessary to explain the calculations of the trajectories. So somebody came up with this idea that there is a planet called Vulcan between the Mercury and the sun. And they also did calculations, and they found that it has to be there, and a large number of people started believing in it. They actually saw it through their telescopes and etc., until about late 1870s, when people realized that it was an artifact of faulty designs of telescopes and faulty calculations. And so truths are manufactured because of what we start believing. And there are many examples even from recent history of science in 20th century. Anyway, so often we fall into these intellectual fallacies, traps of fallacies. For instance, sometimes we are trapped into circular reasoning. A explains B and B explains A. uh, uh, there are false analogy, like I just gave you the analogy of buffalo and crows. There are false dilemmas. Sometimes we think there is no solution other than some right and wrong, but actually there can be multiple solutions available, and we need to work on that. For instance, when you have hostile nations, right? The citizens on both sides, they believe that they are enemies of each other. um, uh, but there can be other solutions, right? So it's not necessary that citizens of one nation have to think of citizens of another nation as their enemies. It is possible to think of everyone as uh, as the same. In fact, people who have fought huge wars like Germany and France, etc., they have realized this fallacy, and they have opened up their borders. Unfortunately, they still make very uh, large weaponry, and countries like in South Asia, we buy that kind of weapon system with huge amounts of expenditure, using resources that should otherwise go to sectors like health and education and etc. Then confusing a correlation with a causal connection. Just because A and B happen together, or say B happens after A, it does not mean that A is the cause of B or vice versa. uh, so for instance, sometimes it is actually sensible. So for instance, we know that tobacco consumption is bad for health. So 50 years ago, it was mostly a statistical observation using medical literature. But today we actually know far more about it using chemical understanding of, or molecular level understanding of how nicotine works on our system. So there actually you do have a correlation, between tobacco and several things like lung diseases, heart problem, and cancer, and etc. But such a correlation does not always work, and one has to be very, very careful uh, when looking at two things happening together or one after another, and thinking that there is a correlation. So anyway, so that's about all I want to talk about knowledge, except maybe one or two more slides. Like here is one that, because of these problems with knowledge, we often we keep moving from one limit to another limit. So one limit could be this gullibility, getting a mail from somebody saying that you have won a lottery for $20 million, and thinking that yes, that is what you have, but then you then you find out that you have been duped, right? And people have fallen for such mails. And then the other extreme is having skepticism about everything. So this other cartoon shows you that someone tells you that 2500 scientists say that we have caused global warming, and you're still skeptical about it, and you say that I would like a second opinion. So actually what happens is we, you know, so this is a scale where we have a knowledge continuum. So we begin somewhere in the middle, and we would like to be absolutely certain about the truthfulness of something or the falsehoodness of something. It's basically the same thing. Knowing that something is absolutely false is the same thing as knowing uh, the truth, because if I know that it is not Sunday, that's a kind of truth, right? If somebody says it's Sunday today, I know it's absolutely false, right? So science as a way of acquiring knowledge empowers us to move towards either end. Now, I'm not saying that scientists claim that they will definitely take you to the end, either to the right or to the left. What I'm suggesting is that it is a method that empowers us to move towards that end. I mean, every institution of knowledge attempts that, but as practicing scientists, I would like to believe that science probably has a better structure, or it's more structured to empower us to move towards either to the left or to the end. So normally when we say that we know something, actually what we mean is that we believe in something. Okay, and so uh, what we can do is we can develop systems of reasoning, logical structures that will provide justifications for what we believe in. Okay, so this is, of course, this is not the last word in philosophy of science, but or philosophy generally. But so you know, uh, justifiable beliefs are as close to the truth as we can get in many instances, not always, many instances. Okay, so we look for justifications. So what are the kind of structures of reasoning we have? There are actually multiple structures, but these are two main ones that we use in formal disciplines like disciplines of science. So one is called deduction, another is called induction. So in deduction, we are given some truth a priori. Okay. So for instance, uh, you have Euclid's axioms in upper primary, and from there we deduce results like sum of three angles of a triangle is 180 degree, etc. Okay. In most things that we learn, we, especially at younger age, we actually deduce knowledge from given statements or given axioms. Whereas induction is a method which, at least till early 20th century, was supposed to be uh, uh, well, till early 20th century, but starting from, let's say, 2 3 centuries back, it was supposed to be the method of science. That is, we keep on verifying principles by carrying out experiments, and by empirical observations we find out that certain things are facts or knowledge. Okay. So the difference between the two is that deduction takes us from a general given idea to some particular fact. So for instance, if somebody tells me that all metals expand when heated is a fact. Okay, so someone brings me a metal and I'll say, okay, let's, we know that if it's a metal, it must expand when it is heated. So that's a deduction. Okay. So because, an idea is already given to us as a kind of a God-given truth, so there's more certainty in it. In fact, by acquiring knowledge, we often mean that we want to be more certain about things. Okay. So there's more of a certainty, but it's less informative than induction, because we haven't really necessarily carried out empirical observations on different metals. Okay, we have believed in the statement that was given to us. Whereas in induction, you bring iron, you bring aluminum, you bring silver, and we test it out, and in each case we find that the metal is expanding when you're heating it. So it is more informative. Okay, but of course, there are problems with it, and we'll see that Karl Popper, questioned this idea that induction is a central exercise in science, and came up with some philosophical dictum. Okay, so science is a way of acquiring knowledge. Now, different people have said different things about it. Richard Feynman, known for his cheeky statements, made a very interesting statement that science is the belief in the ignorance of experts. So that's a funny statement because an expert is supposed to be knowledgeable. How can you believe in the ignorance of an expert? But of course, what Feynman is trying to tell us is that science gives us the power to question. So even if someone claims to be an expert, it could be a scientist with an apron on, or it could be a religious baba, or it could be somebody, older and generally regarded as wise. Whoever it is, science gives us the power to question that. Okay, so that's how Feynman thought about science. In late 19th century, science was thought more, as I just said, more of an exercise to do inductive studies on natural phenomena. And Thomas Huxley, who was called Darwin's dog because he was a strong proponent of the theory of evolution, he said that science is organized common sense. We still use this kind of phrase. We often tell our students, use your common sense, etc. And then he made this very interesting statement: the man of science simply uses with scrupulous exactness the method which we all habitually and at every moment use carelessly. Now, that in a way is correct. I mean, there is, but this idea that scrupulous exactness is is something that has been questioned in 20th century a lot, especially by uh, social scientists. This whole idea of exactness, whether everything about nature and particularly about the human existence, whether it can be studied exactly, is something. Of course, there are people who interpret scientific discoveries wrongly, and there are certain kind of lack of predictability in science. There is, we often use random variables for understanding things that happen by chance, or say there are um, there is a lack of predictability in quantum phenomena, but we know with exact precision and with some degree of exactness how much is the uncertainty in measurement, right? So that way it's very different from what many people interpret it as. um, Anyway, so that is a contestable kind of a statement. Then, of course, we have this wonderful statement by Albert Einstein that one thing I have learned in a long life: all our science measured against reality is primitive and childlike, and yet it is the most precious thing we have. Now, it's a poetic way of saying that among different ways of acquiring knowledge, science is one precious way. And if we really look into the details of the structure of scientific knowledge, then we'll find that it does empower us in many ways to approach truth. Okay, and of course, science as a language. This is different from the language in other disciplines. Uh, Science, theorizing in science requires quantification. Okay, of course, there are gray areas, like there are certain aspects of psychology, anthropology, etc., where you cannot always quantify things. But especially in what we call hard sciences, physics, chemistry, etc., you do not have a theory without quantification. Okay, and the language that we employ for that is mathematics. For mathematicians, that's a rather how should I say? I mean, mathematicians think of mathematics as an art, but for scientists, it is an art as well as a tool, a language to theorize. So you can see how uh, complicated uh, statements in ordinary language can be if you use the same kind of nesting as we do in uh, ordinary algebra. So if you have done middle school algebra, then you know that this nesting, where you have this multiplication, addition, another multiplication, then another addition, then another addition and multiplication, and etc., etc., all this can be done in seconds. But if you read this statement, it will take you some time to figure out exactly what it means. This also has some degree of nesting, in fact, much less than the kind of nesting you have here. The book The Man the Gardener I Employed Yesterday Saw Left is on the table. Okay, so all right. So of course, technical vocabulary requires certain kind of tools and methodology, and there is very little space for ambiguity in science, whereas in other disciplines sometimes ambiguity is necessary. Having multiple meanings uh, is, uh, is a necessity in good art or good poetry. If you had a very clear statement, given in a poem or in a work of art, then it's not regarded as a quality work. And the reason is that multiple meanings coming out of a work of art or a work of literature uh, take us to aspects of reality which are not obvious. Okay, so when we find out the different meanings coming out of it, sometimes in a small poem, you have history, you have politics, you have sociology, you have large number of things, and we can discuss examples if you want to ask me later. But today we are talking about science, so let me not get into all those details. Okay, so now I have already shown you that film about powers of 10, but classification is also a major thing in science. And so here you again have scales, and this is scale in, again, length scale. We are going all the way from 10 to the power minus 15 meters here to parallel universes. Okay, so 10 to the power 28 meters. And you can see that it's a huge time scale of the order of some 44 orders of magnitude. And it's important to classify this length scale into different domains, and indeed you have disciplines. So for instance, if you look at chemistry, it usually deals with anything like subatomic system to maybe something which is small scale chemical engineering fabrication. So that's about from here to here. So from 10 to the power, let's say minus 9 meters to maybe a meter long. That's about it. Unless, of course, you do fossil chemistry or something like that. Then, of course, I mean, also chemical engineering. So that's length scale. And as I had mentioned, you can also think in terms of time scales. Now, physics is more like a discipline of principles. So you have physics all across the scale. Okay, but um, otherwise you have form again, not just physics, formal sciences all across the scale. Life sciences deal with living systems, so all the way from multicellular organisms like bacteria, or unicellular organisms like virus, bacteria, etc., all the way to dinosaurs. Right? So that has its own length scale. And then you have astronomers who look at the details of the larger cosmology. And so you have this kind of a classification. Now, of course, there is no hard and fast boundary. There's no I mean, you could be uh, doing life sciences, and yet you could be a very good mathematician. So or you may be doing research in both the areas, and etc., etc. So the point is that classification becomes necessary because of this vastness of knowledge that science seems to cover. Okay, now if you look at social sciences, right, obviously social sciences have to do with the human scale, right? And the human lifetime is only 100 years, and the human length scale is few meters, right? So it seems to be a very small domain of knowledge, but the complexity of social sciences is so enormous. The uh, uh, the degrees of freedom that our brain has, the way we exercise free will is so complex that the complexity is no less than what we encounter in this entire length scale when we do natural sciences. Okay, in natural sciences you have far greater determinism. uh, of course, I did remember I mentioned that there is lack of predictability of different kinds in natural sciences also. But certainly you have more determinism because you have more well-defined models, whereas in human sciences or social sciences, the models cannot be always constructed so well defined. And when you do that, you are actually using methods of natural sciences in human sciences. Okay, so well, one way of looking at science is to have a practical checklist, and here is this uh, website from Berkeley campus of University of California. So understanding science, and they have a checklist. Okay, so whether or not something is science, you can follow this checklist and decide for yourself. So first, it focuses on the natural world. It aims to explain the natural world, meaning economic ups and downs or man-made structures. That is not the domain of natural sciences. It uses testable ideas. So for instance, an example would be that a sparrow, where does it get its song? Does it inherit or from its parents, or does it get it from nature or environment? So you can test it out, right? You can put a sparrow's egg in some other bird's nest, and then when the baby comes out, you can in the laboratory or in some protected confined environment, you can find out what kind of song it has, and that will tell you whether it is genetic or learned. It relies on evidence. So, in other words, it's not merely a reflection oriented episteme. It involves a scientific community. So, no single person can claim that they have come up with some scientific knowledge. Something becomes a scientific knowledge only when the scientific community accepts it. A good example is how Mendel, when he did his early research in genomics and hybrid plants and all that, he published it, and people looked at it. They tried to reproduce the results. They questioned it, did all kinds of post-mortem on it, and that is how it becomes scientific knowledge. And of course, every kind of scientific knowledge leads to ongoing research. So when double helix was discovered for the structure of DNA, many people thought that that's it, we know everything about biology now. And look at how much biology has evolved since then. Okay, the multiple disciplines that have evolved in life sciences. Okay, so any finding gives rise to more and more continued research. Finally, I mean, this is a bit contestable. There are benefits of scientific behavior. And the reason I'm saying it's contestable is because, especially when people have technology in mind as one, offshoot of science, we know that that's a highly contestable idea, and we'll talk more about it. What science does not look at, actually, what it cannot do. And one of those things that it cannot do is to decide for us what is good for us and what is not good for us. Okay, and of course it can tell us what is not good for us, but whether or not we should continue investigation in something which may not be good for us is not something which science tells us. It's a decision that we make, that society makes, that politicians make, or somebody else. Okay, right. So that's a checklist. Now, typically in the inductivist structure of science, so this is a cartoon that tells you how science is done. We have observations or premises about something in nature, and we hypothesize. And remember, testable hypothesis. We can have multiple hypotheses, and then we carry out experiments to find out whether the hypothesis makes sense. And after repeated experiments, we may come up with some law. Okay, I'll give you some examples later. And then finally, we try to develop a theory for it. Okay, I mean, when I say we, I don't mean an individual scientist or individual research group. I mean the scientific community. So this cartoon shows you the same thing. You define a problem, you form a hypothesis, make observations, test the hypothesis by performing experiments, and then whatever you get, you organize the data, analyze it using machines, computers, etc. If the experiments and observations support the hypothesis, wonderful. Draw conclusions, communicate your results, and inevitably the first time it may come back with referee's comments, but nonetheless, this is how we proceed. And if they do not support the hypothesis, well, it's a temporary letdown. And then you start wondering, did I design the experiments right? Or is it something wrong with my hypothesis? So you design new experiments and you organize and analyze data again. And this cycle goes on. It's a tough life for beginning, somebody beginning a research career, and it takes a lot of hard work and you know many years now to finally be able to publish some good results. Okay. Uh, well, there are some other practical aspects of science that you have to have controllability, meaning if you are looking at observation as a function of, let's say, temperature, nothing else should change during that time. As you are changing the temperature, you're looking at some other property as a function of temperature. Pressure should not change. Concentration of material in the system should not change, and etc. So, I mean, for instance, in pharmaceuticals, they do control experiments. Right now, for instance, for COVID vaccines, there are all kinds of control experiments going on. So you give medicine to one group of patients, and another group of patients you give placebo. That is, you don't tell them that it's not a medicine, it's a fake thing. And then you look at the effect after 6 months. If the effect is the same, that means the medicine has no use. Okay, it's not working. But on the other hand, its effect is such that those who were medicated actually improved, then that means that you have carried out a good control experiment that shows that the medicine is useful. And likewise, measurability. I told you that quantification is a very important practical characteristic of science. Finally, repeatability. What you claim to be a scientific knowledge must be reproducible by different people at different times at different places. All right. Of course, sometimes it happens that you cannot always reproduce everything. Like, a comet was seen in 1680s. How can you reproduce it? Well, you can do calculations and find out when the comet is supposed to come back again, and then wait for that year and see if that happens. So there is a indirect way of reproducing it. Okay, so reproducibility is extremely important, and that is a major practical criterion that distinguishes science from pseudoscience. Okay, so one example is the Copernican revolution. I mean, we call it Copernican revolution, but we now know that ideas flowed across India, China, Arabia, Europe, and in fact, it's silly to classify knowledge as the Indian system of knowledge or the Chinese system of knowledge, etc. Of course, there have been different traditions and different schools of thought and etc. But ideas have gone across the continents from one place to another. So what is now called Copernican revolution, or the heliocentric model of planetary motion, was actually known to astronomers in other countries also, and especially from some literature available from Iraq. Astronomers in Baghdad had drawn the planetary chart and explained the heliocentric model pretty well. Anyway, the point is that there were observations. We all see sun rising in the east and going around the earth, right? So hypothesis could be that sun is at the center of the solar system, and if that is true, then the prediction will be that the Venus size should be uh, nearly the same, because if you have uh, if you have a uh, nearly circular orbit going around uh, the sun, if it was going around the earth, then standing on earth throughout the year, you would see the size of Venus nearly the same. But if sun is at the center of solar system, then sometimes the distance between Venus and earth will be very long. Sometimes it may be very small. So the size of Venus, that is the what we call the morning star or the evening star. Even with naked eye, we can actually see that the size keeps changing throughout the year. So there were many such observations that were piling up, and so Kepler came up with this laws of planetary motion sometime around 16th century. And finally, Newton gave the theory, the theory of gravitation. So the model that Copernicus proposed in 15th century or early 16th century, that became accepted, as opposed to the Ptolemaic model, which was geocentric and gave rise to a lot of anomalies. Now, this process took nearly 1500 years. Okay, uh, at least if you take Copernicus to be the end point of it. Uh, it took about nearly 1500 years to resolve the, which of the hypothesis, whether it is heliocentric or geocentric, which is the correct one. But look at this journey, starting from observations to hypothesis to prediction to law and theory. Today, of course, things are much faster. I mean, in a way, our civilizational evolution has been logarithmic in terms of, how the journey from observation to theory. Today, it can happen within 10 years, for major findings. Another example would be take chemical combination and atomic theory. Now, there were two different hypotheses. Aristotle believed that nature doesn't like vacuum, so you cannot have particles forming matter because, well, what about the space between the particles? In fact, if you believe in modern atomic theory, I hope you realize that this would imply that you are mostly made of empty space, right? I mean, even if you believe in the early 20th century models of an atom with nucleus and electron going around it, do a little bit of calculation for the volume of the atom. Let's say you have, an angstrom, as the atomic radius, and the nuclear radius is 10 to the power minus 15 meter. So cube of the length scale will be the volume scale, and you will find that nearly 100% is an empty space. In other words, I and you are all empty spaces. I mean, that would be a wonderful realization for everyone to have, and many problems in the world would disappear if only we could, uh, uh, we realize that. Of course, in 20th century comes quantum mechanics, and it becomes difficult to say which part of the atom is the empty space, because there is a probability that electrons are present at any given point in the extra nuclear space of the atom. Okay, so this journey from and I mean, as opposed to the continuous matter theory of Arastu, we had the atomists. The Indian philosophy also has mention of it. And Kanad, for instance, the founder of Vaisheshika Shastra, is called Kanad because of Kana, particles. And then in the Jain holy books also you have mention of Anu. So likewise, the Greeks, Democritus, Leucippus, Lucretius, they also conceived of particles. It's like if you are eating an apple, you take a bite of it and then keep taking smaller and smaller bites. At one point, it'll be too small for you to divide it into smaller parts, and you may wonder, when does the appleness of the apple disappear? Meaning, if you keep going to smaller and smaller parts, will it remain an integral apple? Will it taste like an apple? Will it? So yeah, so this is how they also concluded, and they came to this conclusion that there has to be some part of matter which is like the smallest part of matter, and that's what matter is made of. And then it took many centuries to investigate all this, to understand how different kinds of matter they interact, what happens to these particles that form the matter. And also technology had to develop simultaneously. People had to measure precisely as things transformed. See, in 1,000 years ago, it was very difficult to measure gaseous substances, because having a confined uh, gas, I mean, gas confined in a chamber was a difficult thing to achieve, right? And so it was only in 15th, 16th century that people started making precise measurements of chemical transformations as you had reactions. So from there you had new laws of chemical combination, and ultimately Dalton in 1830 proposes the atomic theory, and by 1870 everybody accepts it. And then we know that the end of 19th century and beginning of 20th century were historic days in the history of science. And in 1909 there was this famous experiment by Rutherford and his co-workers, and they let alpha particles pass through a thin gold foil, and alpha particles are doubly charged helium atoms. And so it was at that time that it was possible to have alpha particles, because radioactivity was already discovered by end of 19th century. And well, if the positive mass of an atom and its electrons were evenly distributed in an atom, then the alpha particles would be scattered uh, evenly all in all directions. But what happened was some of the alpha particles had head-on collision and they came back, and some were scattered in different directions. And from there, they interpreted that there must be positive charge, centered in the center of the atom. So anyway, so those are history. So how do we explain natural phenomena in terms of properties of matter? What is there in matter that gave rise to these properties? So questions of this kind kept alchemists and others busy over centuries. And finally, in 19th century, the matter was resolved that matter is actually made of atoms. And then, of course, in the beginning of 20th century, we have, well, it is discrete, but at the same time there is a probabilistic nature to where the discrete particles are located, right? Okay. So there are many such examples. You can think of theory of evolution. You can think of quantum mechanics itself, relativity, and how these changes happen, and from observations to the theory. There's a journey. Okay, this is how science has proceeded. Now, so there are, of course, I mentioned about the practical aspects of science, but there were several philosophical issues. And I heard that you had a wonderful lecture by Professor Basu, who is a philosopher of science, this morning. Um, anyway, so uh, one of the things that was curiosity was that, well, if everything is done by empirical observation, what about sudden ideas? Like there was a story about Kekule, who discovered the structure of benzene, that he saw a snake biting its tail in his dream, and then he thought of the ring structure of benzene. What about that? I mean, obviously, it's not based on any empirical observation. So one way of looking at it is that, well, actually, there is a context of discovery, okay, and there is a context of justification. Uh, you may get ideas, but to actually proceed for a scientific exploration, you will have to justify it using the process of induction, that is carrying out experiments, making empirical observations, and etc., etc. So there is a difference between a context of discovery and context of justification. When we talk about the structure of science, we actually talk about the context of justification. Okay. And then Karl Popper you know had serious doubts about this whole idea of doing science by induction. And so to Karl Popper, the serious question in philosophy of science was to ask what is science and what is not science. Okay, so there were all kinds of claims. Even today, people claim everything to be science. I mean, it's interesting. There are these two distinct attitudes about science. One is that whatever I believe in is scientific. Another is, so what if it is not scientific? Does science explain everything? Now, both of these are rather silly attitudes. It's not necessary that everything has to be science. I mean, life is wonderful without everything being science also, right? There is a place for things that are not science in our life. I mean, thank good heavens that things like poetry and art are not always explained in terms of science. Sometimes people attempt that, but it's not necessary, right? Um, and likewise, science doesn't have to answer everything. No uh, scientist or no science ever claims that every question is answerable. Nonetheless, so Popper asked this question, that what is science and what is not science? And he came up with this idea that it is not the verification by induction that scientists do. Scientists are actually constantly looking for falsifying scientific ideas, sorry, existing ideas. And so a theory is something which is falsifiable. What does that mean? That means you should be able to conceive of a possibility, that you should be able to empirically observe and then say that this falsifies an existing theory. For instance, take gravitation. If you jump out of the window, then you fall down. But you can always conceive of a possibility that maybe somebody jumps out of the window and actually goes up instead of going down. Now, if you can empirically observe such a thing, you will say that theory of gravitation is false. right? So this is what the scientists must be doing, and it's very interesting. I mean, another example I can take is, say, the theory of existence of God. Now, it's a very powerful theory and very important theory. It has held civilizations together. It has given us a moral fabric and everything, right? But is it a scientific theory? Now, it is not a scientific theory if you understand falsifiability, because you cannot conceive of a possibility where God's existence can be falsified. If you say God is benevolent and somebody has an accident, and you say that, well, that's it, it's falsified, then you'll be told that no, God is testing your will. So now there is nothing. See, usually what happens is people get upset about, people start taking positions, whether this is right or wrong. It's not a question of right or wrong. It's a question of whether something is science or is not science. And as I said, just because something is not science does not mean that it needs to be thrown away, or it has to be undermined. That's not the issue. The issue is what should be called science and what should not be called science. So that's what Popper said. And so I think what I'll do is I'll stop here and see if you have any questions, and then we can take a little break and come back at 3:30 for the second session.
Thank you, Professor Singh. Uh, it was lovely hearing you. And if there are questions, please, you can unmute yourself and ask, or you can put it in the chat box, in the chat section. This, this is to the participants. If there are any comments, if there are any questions, please ask in the chat box. Or you can unmute, ask your question, and then mute again.
Looks like people are thoroughly bored, huh? Nobody has any question.
Yes, yes. So it's a lovely talk, very interesting, but I don't want to ask questions myself. Yeah, there are many things which we can discuss, but I want the participants to take
Sure,
part.
sure, yeah.
Yeah.
So the participants are our college and university teachers, right?
That's right, and some research scholars too.
And some research scholars. Okay. Well,
In
if
fact, the way science is taught in our system is we train our students not to ask questions,
hmm,
and this goes a long way. And this is the problem we have. There are many
hmm,
things you are given to believe
hmm,
that whatever is said by the teacher or the speaker is absolutely right. And
hmm,
there are various things which we just don't stop to question.
hmm, hmm,
Even that Newton's law of gravity, it comes as a gospel truth that you have when you have any two masses, they
hmm.
attract, and that force is proportional to product and inversely proportional to the square of the distance. Uh, that is an empirical formula which Newton got, but we
Okay, there
never.
is
Yeah, there are some questions.
there's a question. Yeah, so see, just like you have language that initiates you into some area of knowledge, like you read something and then you say, oh, I never knew this, and you start learning more and more about it. Similarly, emotion initiates you into learning of things. Now, of course, we often say that you need to be passionate about whatever you're doing. Say you're doing an experiment, or you're solving a mathematical problem. If you don't have passion in it, then you will not be able to do it, because after a while it will become a drudgery. But that's not the only thing. Wha- wha- yeah. uh, Sorry, just one sec. Let me answer that question. So what emotion does is it initiates you into questions that you normally do not think about. Okay, so for instance, there can be multiple aspects of the same question. The good example I give is just Ambedkar Nehru cartoon, which started a huge debate about 8 years ago. It was there in a NCRT textbook, And so some people thought that it's not good because Ambedkar was shown on a turtle, and this was a cartoon that was drawn by Shankar. If you do Google search, you will find it. And so Nehru is standing with a whip and trying to move the turtle. And because Ambedkar was the chairperson of the drafting committee for the constitution, so people of India are waiting for the constitution to come. Now, there are two ways of looking at it. One is the children can look at the cartoon and they will find it very interesting. They will, start learning more about it. The other is that, somebody may start making fun of the whole situation, and it can be quite traumatizing for, I mean, quite a trauma, quite agonizing for someone coming from deprived castes. And so how do you, what is the truth about this now? Without making a statement about what is right and what is wrong, what I would like to say is that how you emotionally connect, with the issue tells you what you learn from it. Okay, so if you have no emotional connection, you will not even approach, that area of knowledge. So it is in that sense emotion is extremely important. So I can give you other examples also. I hope this gives you some idea. Thank you for asking this question, Mr. Baburao. Anybody else? Okay, so I think you can keep thinking about questions. We can take a little break and come back, and we can start with any questions you have, and then we'll move on. Is that okay, Professor Hassan? Najam, is that okay?
That's perfect. Let's
Yeah,
stop for a while.
yeah,
Uh, uh, with 3:30, shall we come back?
yeah.
No.
3:30.
5 minutes from now, it's 15:23. Yeah. Yeah, so what I was saying then was about this gravitation too. Hello, can you hear me?
Yeah, yeah, yeah. Yeah, I can hear you.
Yeah,
I
so
have the other speaker on, so I can hear without the phone.
so in schools and all, many things we are just given to take it on face value and believe it is true. We are never asked to question it.
Yeah,
Like Newton's law itself is obviously flawed because there is no aspect of time involved in it. What it says is gravitational effect travels at infinite velocities. But if there's something goes wrong to sun now,
exactly.
expecting that something will go wrong, I mean, the effect will be felt
Instant.
by Mercury and Pluto at the same moment is absurd.
Mm. Mm.
But we are never given to accept that. I mean, we,
Mm.
we just accept it blindly without
Yeah.
questioning. And then what you said about belief and knowledge, and it is really, really interesting. What you believe is, you think is true, and isn't it?
Yeah.
Yeah,
Yeah.
people tend to.
I mean, unfortunately, that's those are the times we are living in,
Yes,
when you can see it all around us.
yes, and that gullibility and issue also.
Skepticism. Yeah.
All yeah, skepticism. There's all kinds of weird things which come on WhatsApp, and people are ready to believe it. But
Yep.
anything sensible, they are skeptical about it. They doubt
Yeah.
it.
So did Prajit talk about Popper and Kuhn and all?
He mentioned a little bit, but not in detail.
Acha.
Yes, yes. Yeah, he did. He did touch upon.
Hmm.
So maybe we can start
Yeah.
now.
Yeah. So let me know when I should begin. Huh?
I think we can begin now. We have given.
Right. Okay. So I hope everybody is back, and I hope you have been thinking about what we have discussed so far. So I have been rather slow so far, and now I'm going to speed up. Okay. So I mentioned to you about demarcation as a major problem in philosophy of science and falsifiability as a philosophical criterion of science that Popper, uh, you know, uh, told everyone. Now, in this kind of a way of looking at science, there is no place of history. How do scientists, how do they do science? And if you look at history of scientific discoveries, what do we learn from there? So there was this guy, Thomas Kuhn. He was actually a physicist and then became philosopher of science after his PhD from Harvard. He did some studies on history of science and he came up with remarkable insights, and he published this book called Structure of Scientific Revolutions, and in 1962 or 63, something like that. And so in like one sentence summary of the entire book is, what he says is that at any given point of time, scientists do what is called normal science. That is, there are certain theories existing, and most scientists just keep on working within those theories. If things don't agree with theory, they usually think that they have done something wrong. And this is how most science teaching also happens, right? If a student finds something weird in the laboratory experiment, the teacher would simply say that, no, no, you did something wrong. And and never an anomaly is reported in a science lab course, right? So what does not agree with existing theories is called anomaly. And sometimes what happens is these anomalies keep piling up. And then some people start wondering whether there is something wrong with the existing theories. And then new theories start developing. This is called a paradigm shift. Unfortunately, the word paradigm is not as popular in natural sciences as in social sciences, because it's in the history and philosophy of science that people talk about this, and also in other areas of social sciences. So what happens is when this new paradigm happens, that's called a paradigm shift. So let me show you a little video clip to explain this. It's a very interesting video.
One way to look at scientific progress is to see the world as a collection of facts represented by these pom-poms.
Oh, you'll have to share the. You'll have to share
Yes.
the. Can't see.
Yes. Okay. Okay. Thank you for reminding me. Sorry, I share screen. No, it does say share computer sound. The sound is not coming, is it?
The sound is coming, but not this video.
Oh, okay, okay. This, okay. I thought I shared my desktop. No, no.
Yeah, it's now we can see what powers of 10.
Shared window is closed. Why is the shared window closed? Just a second. Share screen, desktop. Desktop is shared. And let me restart this. Is this happening now? Can you see the video?
Yeah.
Okay.
One way to look at scientific progress is to see the world as a collection of facts represented by these pom-poms. We may observe these facts and add these observations to those we have already made. And so it appears that progress is a process of addition. However, the philosopher Thomas Kuhn argued that observations do not exist in a vacuum. Instead, they are contained within a theory. The theory is a story which explains the meaning or significance of the observations. The dominant theory in a discipline at any given time is called a paradigm, and the observations are placed within that paradigm. A problem occurs when observations are made that do not fit into the paradigm. A crisis is reached when too many of these new observations do not fit into the old paradigm. A new theory is then proposed. If this new theory contains the observations better than the old theory, then there is a paradigm shift. The old theory is then destroyed. And replaced by the new theory. To Thomas Kuhn, scientific progress is as much about destruction, specifically the destruction of the old theory or paradigm, as it is about the addition of new observations. And even this new paradigm will only last until it suffers its own crisis.
So in the early edition of the book, the first edition, he did mention that the old theory is destroyed, but then a lot of criticism followed, and then in the later editions, Kuhn has corrected many of these statements from before, and of course, the old theory is never destroyed. Because it did explain the world, the cosmos in a certain way. So what happens is a larger theory, which kind of subsumes the older theory. So when quantum mechanics came into being, it's not that classical mechanics is destroyed. What it means is that classical mechanics becomes an approximate domain, right? For larger objects, large objects, classical mechanics works fine. Similarly, relativity for things that are not moving very fast, the non-relativistic mechanics is fine, and so on. So it's not like the older theory has to be destroyed. Anyway, so that was Kuhn's way of looking at it. Then, of course, I put these dots here to imply that there have been several modifications of it by later people, Lakatos and others. Okay, so and then the other philosophical issues related to science came mostly from questions on the structural foundations of science. Uh, if science was an objective, is an objective way of looking at things, then why is it that we don't have, representation from every kind of community in the scientific profession? Of course, there are multiple ways of answering this, but nonetheless, feminists have really questioned the foundations of science, and some of it probably you will hear in Professor Prajwal Shastri's talk, and also Dawn Cruiser's talk tomorrow, day after tomorrow, about the issue of ethics in science. So those are serious philosophical problems. Often we respond to this by saying that, well, it's because the ideas have been implemented wrongly, or because the social structure is already full of discrimination and prejudices, and that is visible in science also, which is embedded in the larger social structure. So there is a strong program that evolved in a place called Edinburgh in England, where they have been suggesting that this kind of a criticism of science, which can be uh, answered by saying that, well, it's not the problem of science, it's the problem of society, is a weak criticism. So there are stronger criticisms of science, and it's called the strong program. I'll talk a little more about it when I come to sociology of science. Okay, so this demarcation problem, let's come to it again. What is science and what is pseudoscience? This cartoon slightly hazy, but if you can read through it, it says crossing the line from alchemy to chemistry. So one alchemist is asking another alchemist, you have turned lead into gold. Good, do it again, write a detailed description of how you did it and submit it to peer review. Now, in other words, science has a very serious community check on claims of discovery. Um, no one person can claim that they have come to realize or come to make a discovery. Whereas in pseudoscience, you cannot have reproducibility. So astrology can work for somebody, but it cannot work. It does not necessarily work for everyone. So I mean, if it makes someone happy, it's fine as long as they don't hurt themselves or others by practicing it. So there are many such things which are pseudoscience in nature, where a claim is made that it is scientific, but it is actually not science. Okay, it does not satisfy the practical and philosophical criteria of science that I mentioned. So, for instance, homeopathy is not a science. And the reason is that claims made on homeopathic discoveries were not reproduced when a team of scientists went to a famous lab called, the person was called Beneviste. He died just about a few years back. So he had claimed that the reason diluted solutions in homeopathy work really strongly is because after some level of dilution, the water molecules start acquiring the shape of the steroid or whatever is dissolved in it. Now, this does not mean that you don't take homeopathic medicine. If it works for you, it's fine, but it can be very dangerous because it is not science. Okay, as I said, it does not satisfy the criteria of reproducibility. Other schools of medicine, other than modern medicine, for instance, Ayurveda, Hakimi, Unani, etc. Now, many of these things have been scientifically tested. So, Ayurvedic medicine, most of them are known to be good for you scientifically. But the philosophical foundations of Ayurveda have nothing to do with modern science. Okay, so in the sense that this idea that the body is equilibrium of different tendencies like kapha, vata, and pitta, and when this equilibrium is disturbed, you need to take some medication to bring the entire body into equilibrium, is something which cannot be tested scientifically. So that remains a problem. But otherwise, the medicine is known to, heal, and it has been scientifically tested, which cannot be said about homeopathy. Okay, yeah. So there are issues that sometimes make people unhappy, but that's how it is. So in pseudoscience, there's a lot of vagueness, and ad hoc exceptions are made to to claim that a theory works. So this cartoon is saying that what's nice about working in this place is that we don't have to finish any of our experiments. Okay, so that's, I mean, one reason people get upset is because there's a lot, usually people are made fun of when they believe in ideas other than let's say modern medicine. But it's not a question of undermining something or making fun of something. It's, as I said before, it's a question of what is science and what is not science, and what is harmful and what is not harmful. Of course, somebody may say that, well, science has been harmful to us in many ways, and that's probably true. But but still, something is science and something is not science. Okay, sociology of science. So, one of the founders of modern sociology called Merton. So I think his name was Richard Merton, I think. Yes, something like that. Yeah, so these Mertonian norms are known after him. In fact, he died not many years back, like 2003 or something. He was a professor in Columbia University. So he says that these are the norms of the, sorry, oh, okay. These are the norms of the social profession of science. By communism, this doesn't mean the communist communism. It means that there is a community ownership of scientific goods. Okay, so there's no individual ownership of scientific discoveries. So there has to be a collective collaboration. And secrecy is the opposite of this norm. So what happens today with corporate science, there's a lot of secrecy, even with COVID, as data is being shielded from country to country, and, claims are being made that, data is being stolen. And this is all silly, because science is really a human endeavor, and there should not be any secrecy about it. Then universalism, scientific validity is independent of the socio-political status or personal attributes of its participants. It doesn't matter whether you are a scientist in a communist country or in a capitalist country, or whether you are Hindu or a Muslim or Sikh or whatever. Uh, Science is science. I mean, that's how it should be. This is what Merton said. Disinterestedness. Scientific institutions act for the benefit of a common scientific enterprise rather than for the personal gain of individuals. So there has to be a detachedness. And then there's an organized skepticism. Scientific claims should be exposed to critical scrutiny before being accepted. In other words, again, kind of falsification, importance of falsification. And this should be both in methodology as well as in institutional codes of conduct. Now, this was, of course, kind of a very idealist way of looking at science. And of course, in 20th century, this has been criticized heavily. And so when it comes to applying science to society, as I just mentioned, Kuhn had pointed out that science is not really, such a exclusive, ideal way of doing things. People actually work within a given theory. In fact, so scientific discoveries are theory laden. Okay, that a theory determines what you are going to discover. And then there are scientific revolutions when there is a crisis in existing paradigm and new theories start emerging. So it becomes questionable that there is a rational structure to science, because the community behaves as if they're practicing a religion, and the only when there is a crisis there is a paradigm shift. This way, actually, science is very different from traditional religions. In traditional religions, crisis gives rise to new religions. Okay, denominations evolve. So from Catholicism, you have Protestantism and so on, right? Uh, and there is hostility. But when paradigm shift happens in science, there may be individual hostility, but in terms of community, nothing like that happens. So, and then, of course, there is a problem that scientists want to look for a theory of everything. So there's a constant attempt to have unified theory for everything, whereas truth may not be something which can be fit into a single mold. Okay, there may be different kinds of truth depending on, the culture, the tradition, etc. So finally, science and scientism. Being scientific does not mean that you have to be, religious about science. That you have to put down everything which you think is not science. I mean, often that happens to many people. So that kind of scientism is also not very good. I mean, Richard Dawson was probably one example of this, and he strongly denounced everything which was not scientific. For instance, you can see on YouTube his film on homeopathy and other claims of medical remedies which are not modern medicine, how he denounces them. And sometimes it comes hard on people. That may not be a good thing necessarily. Hazards of science. Well, of course, people usually point out the so-called atom bomb, Nagasaki, Hiroshima, but that's not the only thing. Eugenics, believing that certain genetic traits are superior to others, and hence protecting individuals of such genetic traits, and marginalizing others. Recombinant DNA technology, for instance, the claim that the COVID virus may have been created in a lab. Okay, experiments with animals. Sometimes we are very cruel to animals, and sometimes with humans, and so on. And in fact, when Lord Rutherford was once asked what is science, and he said, science is what scientists do. Too bad, it could be bad for you, it could be good for you. So there are problems with science, right? For instance, in the USA in 1940s, teenage boys were fed radioactive breakfast cereal to find out what effect it has. Middle-aged mothers were injected with radioactive plutonium. Prisoners had their testicles irradiated, all for science, progress, and national security. And until 1970s, such experiments went on. In India and many third world countries, women were treated as guinea pigs for all kinds of harmful contraceptives. So, there are issues with science. And simply speaking, there are structural problems in the very origin of modernity and modern science. Modernity is, again, where a human being is dissociated from nature, and victory on nature becomes a major goal of human existence. And modern science, unfortunately, is simultaneously it evolved with modernity. Often people treat them as synonymous. They are not really, but anyway. So is science really value neutral? So if I close my eyes and you ask me to name a scientist, am I likely to name a woman scientist, or anybody who is not a white European scientist? Is science really for the welfare of humanity? If it is motivated by the victory of human over nature, can that be good for human beings if we destroy nature? A scientific model of development was seen as a sure way to prosperity. In early 20th century, there was this hope that things are going to become scientifically managed. And there was this guy called Taylor who thought that everything can be scientifically managed. Factory workers, their behavior can be scientifically recorded. The management can be scientifically instructed. And so it's a very interesting theory that, if everything is done scientifically, it will be a wonderful world, and there will be large, amounts of production and of goods and etc. But it did not really happen, right? Okay. So you can have all kinds of, views on this. So one answer to the question, is science really value free, would be that, well, unethical applications of science do not prove that science is not value free. Okay. So that is the weak program, kind of weak criticism, right? And but they show that there is something ethically objectionable about scientific knowledge itself. So you have these views which appear kind of contradictory. I put them together just to let you think about it. Science provides knowledge about nature, and what society does with that knowledge is not a question of science. Okay, so science does not prescribe morals. Okay, the ideal of value neutrality is unattainable. Scientific inquiry is inevitably laden with value judgments. Okay, scientists choose what they have to study. Value judgments about relative importance of different possible objects of study have to be made. How can scientists just get away from this serious issue? I mean, they are also parts of society. They have to take responsibility. So any set of data in principle can be explained in more than one way. The scientist's choice of theory is not uniquely determined by data. Values are inevitably involved in the theory choice. Okay. Scientific research today is funded heavily by private enterprises who have vested commercial interests. So scientific knowledge cannot be divorced from its intended applications in the way that value neutrality requires. We cannot say that corporations are interested in value neutral applications of science because they are profit making bodies. Okay, so science has these limits. Again, this is a very simplistic way of saying things, that science will not do moral judgments. It will not do aesthetic judgments. That is, it will not tell us what is aesthetically appealing, good art, or good music, bad music. Those are, things that we train ourselves to understand, or we cultivate within ourselves. And of course, it cannot give you conclusions about supernatural explanations. Remember that it focuses on nature. It aims to explain natural phenomena, not supernatural things. So if anybody says that they have a scientific explanation for some supernatural thing they have in mind, they don't know what science is. Okay, so until now, scientists have had little or no understanding of how science actually works in practice. Most scientists think of science ideally. I mean, in their individual life, private life, they may be living completely unscientifically. But about science, they have this ideal kind of utopia kind of notion, romantic notion, that they believe it magically produces neutral, value-free, and universal truth statements. Scientists until now have thought that they operate in autonomous environment protected by state funding. In reality, funding for science increasingly comes from corporations and foundations, and obviously, anybody who invests wants to make profit, right? So they have vested interests in the research agenda. Scientists thought that the sole purpose of research is to advance human understanding and knowledge. In reality, science is driven by military interests, need for corporations to make profit, and those concerns of the public that cannot be politically ignored. Scientists tended to believe that science can be pursued for its own sake. It should be esoteric in content, accountable only to itself, with no concern for social or cultural issues, and it should be publicly funded. But that's not how democracies work. Okay, so scientists have to be accountable to the rest of the society. And scientists have presumed wrongly that if public were to have more technical knowledge, it would accept what they say implicitly. The public is often concerned with questions of ethics and policies and risks and safety. So having technical knowledge does not necessarily mean that they will accept science easily. As we can see in many Western countries, especially USA, uh, there's a lot of technical knowledge that the average American citizen has in terms of modern science and technology, but that does not mean that they have accepted a scientific way of looking at things. So what is the strong program? The strong program is strong sociology. Again, it's a largely Edinburgh-based school of thought, and it's the few names prominent in this are Bloor, Barnes, Collins, Mackenzie, and Henry. So, um, so they it's a variety of sociology of scientific knowledge, SSK, and so what they say is that it's a reaction against the weak sociologies of science, which restricted the application of sociology to failed or false theories, such as phrenology. Phrenology is a measurement of the brain size. Okay, so some people used to dig up, graveyards and get human brains and fill up with mustard seeds to find the volume of the brain, and then claim that certain race is superior to other races because they have larger brain size and etc. So, of course, these have been proved to be false biases. and they had covert political or economic interests. So strong program proposed that both true and false scientific theories should be treated the same way. Both are caused by social factors or conditions, such as cultural context and self-interest. All human knowledge, as something existing in human cognition, must contain some social components in its formation process. In other words, you cannot uh, get away from the baggage of your tradition, your culture, your value structure, right? And so every knowledge production is socially constructed. So this is what the strong program tries to prove. And the requisites of a strong program analysis are that firstly, they try to understand how a certain kind of knowledge has been produced. So what is the psychological, social, and cultural condition behind it? And they examine successful as well as unsuccessful knowledge claims. So there's an impartiality about it. And the same types of explanation are used for successful and unsuccessful knowledge claims. So there is a symmetry. Okay. And finally, they apply the sociology to their own ideas. The same critique is applied to themselves. Okay, so now when all this was going on, the feminist critique and the strong program, etc., so some scientists started getting really upset because what the critique was suggesting is that there is a rationality in every tradition and every culture, and there is no universal or a grand narrative. Okay, so when you say theory of gravitation is independent of what culture or what religion you're from, so the critique had developed to an extent that people started saying that this is not true. Every kind of knowledge is culture dependent, it's relative. So it's called cultural relativism. So Alan Sokal, a theoretical physicist, a very progressive, left of center, politically thinking person, he wrote a long paper which is called Transgressing the Boundaries Towards the Transformative Hermeneutics of Quantum Theory. Hermeneutics is philosophy of aesthetics, okay? And it was published in the most well-known social science journal in USA in the summer of 96. After it was published, and it had large footnotes, and the footnotes included, feminist comments and etc. So the footnotes themselves would be roughly about 12 pages of the article. When it was published, he called a press conference and he told everyone that it was a farce. Everything written in that paper is fraud, and there are things written which even a college student of science should be able to defunct. And so then, of course, there was a lot of uproar, and people in social sciences were very unhappy about it because they had a special edition of social text called the Science Wars, where this article was published. So, of course, you can go to Sokal's site and get a lot of information about what Sokal has to say. But I'll just point out 3 or 4 things that he said. He said there exists an external world whose properties are independent of any individual human being and of humanity as a whole. These properties are encoded in eternal physical laws. So in other words, he's saying that, look, there are things which you have to accept, which have nothing to do with, relative, which are not relative to a particular culture or tradition. Human beings can obtain reliable, albeit imperfect and tentative knowledge of these laws by objective procedures. Objective, see, this, this is important because that is what social scientists have been questioning about science, that is science really objective? Um, so what he's saying that no, these laws can be tested objectively, prescribed by epistemological strictures, that is theory of knowledge strictures of the scientific method. Anyone who believes that laws of physics are social conventions is invited to try transgressing those conventions from the windows of my apartment. Meaning, so he was staying in New York on the 21st floor of a building. So he's saying, come and jump from the window and find out that theory of gravitation holds. Okay, that's what he's trying to say. But anyway, the point is not just to laugh at the critique of science, but to realize that it had gone too far, and things which do have some universal nature, some fundamental theories of science, even those were being criticized on the grounds of social construction. Okay, so there is a distinction between the natural and the human sciences. In the human sciences, there are many things which should not be a part of nature. For instance, self-consciousness. Okay, the natural sciences work should keep the observer as far away as possible. It is progressively becoming more possible in the sense that, now you can do lots of measurements using a machine. Sometimes, of course, the idea is misused. For instance, medical treatment has become very costly because a doctor relies on more on findings from a machine. You're asked to do, you know, a dozen tests, right? Blood test, whatever, MRI, and you know some CT scan, and etc., etc. Whereas earlier, when I was a child, all these machines were not there, and the doctor would just look at your pulse and look at your eyes and prescribe you medicine. So yeah, so it has become possible more and more to take the human or the observer as far away as possible from the observation. Whereas in human sciences, that's not possible at all. Self-consciousness is a fundamental characteristic of human beings. Okay, so even in animals, we find that dogs bark at their images on mirrors. Male birds during the mating season, they keep hitting window panes, thinking that there's a rival courting their female cohort, and so on, right? So self-consciousness is one thing. The effect of observer is far, far more prominent in human sciences in all areas, like economics, for instance. Depending on whether you are a bull or a bear, meaning you're an aggressive investor or a very careful investor, the stock market's price will keep changing, right? So there's an effect of observation on what you're observing, right? Similarly, when you have these instances, these mental health issues where some people claim that some spirit has entered their body, and there's a whole societal phenomena. There's business interests. There are all kinds of things associated with it. Okay, whereas actually it should have been just a case of ordinary mental health illness, and it should have been treated like that. So, but the fact that it is being observed by others, that affects the person who is undergoing that mental health problem, and sometimes they start believing that they are actually under the effect of spirit, Devi Charana, or things like that that we say. So more examples can be given if you ask for it. Okay, so in other words, there are distinct you know uh, differences between the natural and the human sciences. An observation in human sciences is subject to multiple interpretations. So you see an animal going to, let's say, a deer or something, going in a forest, going to a pond and drinking water. The natural science observation would be that the animal is thirsty and so they're drinking the water. Whereas in social sciences, human sciences, if a human being takes a glass of wine or water or whatever, now you can interpret this in many different ways. You can say the person is happy, so they are drinking. You can say the person is unhappy, so they are drinking. You can say that something has happened to the person, you know, uh, during the day. Um, they may have had a fight with somebody, or they may have had good conversation with somebody. I mean, you can have millions of interpretation. So yeah, so there are distinct differences between the natural and the human sciences. Nonetheless, many human sciences disciplines are becoming more and more uh, organized with the methods derived from natural sciences. So, for instance, predicting the poll results, election polls, etc. More scientific, quote unquote, scientific methods are being used for such purposes. Okay, technology. Now, I included technology in this talk in Science as a Way of Acquiring Knowledge, because most people think that there is an intimate connection between science and technology. And in a way, science has that awe or that glory because of technology. In fact, when in school we are asked to write an essay on science, whether a blessing or a curse, we in fact talk about technology because we don't know much about science, right? So we talk about medicine, we talk about bombs, we talk about all kinds of things. So so let's talk a bit about what is technology, and then I'll move on to science and technology. So what is technology? So normally we think of technology in terms of the marvels or the hazards. And when technologies fail, they do so in a big way. So here, the two pictures here. One is the Bhopal gas tragedy, 1984, and the other is the Fukushima tragedy, which happened just about 6, 7 years back. But in spite of all these major failures, still, if you ask people uh, whether there are positive achievements of technology or you have harms from technology, most people would actually count the positive achievements more than they would count the negative ones. Okay, so somehow it seems that our mind has become, it has become prone to living with technology rather than rejecting it. So where does this come from? Is it just a faith, or do we actually understand what is technology? In fact, when you look around yourself, wherever you are sitting, look around and look at the technology, the paint on the walls, the ceiling fan, the computer that you are listening to, or the mobile phone, etc. If I ask you, well, how much do you know about this technology that you're using? Now, you maybe, I mean, not just you, I or you, anybody, we may be able to say a few things about it, but beyond a certain point, it is something which we don't understand. Okay, in fact, most of the things around us, so lasers, microprocessors, gene splicing, nanomaterials, these are of course more sophisticated things, but even ordinary things around us, we understand very little of what we are using. And so inability to understand technology and its effects is a great problem of our age. Okay, just this morning I had misplaced my phone, and I was like, for half an hour I was going berserk, not having the technology and not being able to replace it immediately, a misplaced phone, gives rise to an existential crisis, right, in all of us. But however, we can understand major causes and consequences of a technological change. Okay, let's try to do that. Okay, so first thing, the fact that we can employ technologies, it sets us apart from other creatures. Actually, many other creatures also have technologies. So, for instance, chimpanzees, they use, straws as pipes to bring out termites from tree bark and eat them. Or, beavers, they make nests in, around flowing water. Or oysters are broken by the otters, right? They take rocks and they break the oyster shells. So you can find YouTube images on all these things. So we do, and birds, of course, wonderful nests that birds make. I mean, what a sophisticated technology. Okay, many of these things we cannot do ourselves that easily. Okay, all right. So, but uh, and also we do not have many capabilities that many of these many animals have. Like for instance, we are not very strong, certainly not like an elephant. We can't run very fast like cheetah, let us say, or we can't fly like a bird. We can't stay in water for too long, right? uh, but we have survived on this planet. Actually, if we did not have technology, our species may have disappeared, right? So compensating for the physical weakness, for the sake of survival, we have intelligence, and that is a source of technology. So in other words, in spite of all the harms of technology, we can't really get rid of it. It is very natural. It is inane to us that we live with technology, and we continuously keep designing new technology. Okay, and without the capacity to invent and use variety of technologies, human species could have uh, become extinct. Okay, we will not be surviving on every part of the globe. So reliance on technology is as old as humanity itself. So one of the early discoveries in technology is, of course, the fire and then the wheel, right? Now, what is important is to keep in mind that when human beings discovered fire, they did not know the science of fire. When they discovered wheels, they did not know how rotational motion is converted into translational motion, right? All these things came much, much later, centuries later, right? Okay, so I mean, the reason I'm mentioning that is that we should get out of this simple notion that science applied becomes technology, because without even knowing science, human beings discovered technology. Okay, now beyond the tools and techniques, that is the hardwares and the ways of manipulating them, you have something more about technology. Development, production, and employment of particular technologies, they require a group effort. Okay, now, and that means, take a simple example like a village potter. You need a complex network of material suppliers, potters, tool makers, marketing agents, and consumers capable of making good use of the pots, and etc. If you take a complex technology like a computerized manufacturing system, obviously you need large number of people in a coordinated fashion. So this organization is like a software that controls and guides integration of diffuse human and material inputs. Okay, so there's a whole system of technology. Okay, devices, skills, and organizational structures. So for instance, a historian of technology has said that the first machine was the organizational structures that Egyptian pharaohs employed to build the pyramids. Those were the first machines. Okay, right. Okay, so normally we look at technological advance as, technology develops in a dynamic way, that is, it keeps moving forward, and in a cumulative way, that is, every advance is added onto, new frontiers, right? So in the beginning, it has a slow rate of growth, and then suddenly the rate of growth, so this is rate of growth, and this is time. So not growth itself, rate of growth, how fast the growth is changing. And then it reaches a plateau, but by the time it has reached a plateau, the rate is already pretty high. Okay, so, and then of course, technologies come and go. Sometimes old technologies die down, new technologies come, but the cumulative effect remains, right? So new technologies grow based on, the knowledge that we have from old technologies. Okay, now technological progress does not mean that there is a general progress. I will elaborate on this a little more, but before that, let me tell you about two different views of technology. Similar to science, there is a view that much of technology is socially constructed. And in fact, it holds far more clearly for technology than for science. And another view is determinism. And that is technology advances according to its own inner dynamic, unrestrained by social arrangements, systems of governance, culture, and thought. In other words, we are servants of technology instead of its master. In many ways, this is true about computer technology. Okay, in the beginning of the last decade of 20th century, those of us who were theoretical scientists, we knew what was happening in the world of information technology. We were among the first ones to use email and, internet and etc. And but when we told this to our friends who were in this development sector, or say in sectors where disseminating information is important, many people didn't believe in us, and many people thought that, well, no technology is good for people, and it is eventually going to be against people's interests, and etc. So, but we knew that we are not going to be, you know, uh, and we can't live without it. This became very clear to those of us who were using computers heavily. Um, so, it exerts a great influence on social, political, and economic relationships. Everything from antibiotics to zippers has affected our lives to some degree. The social construction view says that emergence of particular technologies, or choices between competing technologies and how they are used, all these owe a great deal to socially grounded forces like political power, social class, gender, and organizational dynamics. Okay. And humans are social creatures, so technological change is necessarily a social process. Even about computer technology, it is said that in the beginning, the industry or defense sector, they were not that greatly interested, except when the wars were being fought. then of course it was important to decode what the enemy, the signals that enemy is sending to its soldiers and etc. And there are films made on it, on Alan Turing, and decoding and etc. And of course, during the Second World War, as the American boys went to Europe to fight the war, and also the Eastern Front, uh, the um, women were left behind to write the programs and etc. And it was actually at the end of war when the first electronic computer came, the ENIAC, the electronic and numerical integrator. So that was 1946 when ENIAC came into being. So at that time, the interest was not that great. But once it became obvious that it has a potential, the research and development in computer science or information technology was heavily funded by military. And so initially, internet was used by scientists from the CERN, for instance, the nuclear research, the international nuclear research effort in Europe, because scientists wanted to communicate their data. But the moment it became apparent that it's of value, American defense took over, and for a long time, nobody knew what developments were taking place in internet technology. It was only in early 90s when it started becoming apparent to everyone. So yeah, so there is a social aspect of even computer technology, which seems to be largely deterministic as opposed to many other technologies. So there are different effects of technological changes. So, take the big dams, Narmada Dam, for instance. If you ask the sugarcane lobby in Maharashtra, or rich farmers in Gujarat, they will say that it has been very beneficial to humanity. And of course, the government supports that claim. But if you ask the tribals who were displaced from their villages, you will get a very different story. I have been to a town called Harsud, which is close to Khandwa. The entire town was submerged to form a water tank for the Narmada um, Valley project. And so, people like you and me, when we are displaced, we can go and live elsewhere. But uh, ordinary people, especially tribals who live in a self-sustained forest kind of economy, when such people are displaced, they have nowhere to go. Um, I mean, as it is, the rehabilitation policies, etc., in our kind of system do not work very well. But that is a separate issue. But even after they are rehabilitated and they are, uh, put somewhere else, the men don't do any work anymore. They become, drunkards, and even little children become subject to exploitation by drug mafia, liquor mafia, and you can see such children roaming around in towns like Delhi, Chandigarh, etc. So yeah, so it has different effects on different sections of society. So technology has a subversive role. It restructures power relations within a society. Wealth and income is redistributed, and human relationships are altered. Um, Example after example can be given on this from all over the world. Some technological changes are massive and they lead to vast social restructuring, and technology does not yield its benefits without exacting a cost. So progress, yes, but at what cost? So for instance, before the Second World War, technologically the most advanced country was Nazi Germany. Now, in terms of human civilization, is that a progress? Something worth thinking about. I mean, there's a lot of talk about technological advancement in our country today, but is that necessarily a progress for our people? These are very serious questions to worry about. So a lot of people think that there are technological fixes for problems. So for instance, if there is a problem of drug addiction, then you have a methadone treatment. Okay, now, or say if there are traffic accidents, you have this bubble, the balloon that swells up, and so there is a technological fix, to save people from accidents. But actually, the technology is not really addressing the root cause of these problems. So, drug addiction is not just a health problem, it is a social problem. Which sections of the society are more likely to become drug addicts? Well, the poorer people, the marginalized people, the young people. Why is this happening? Unless we address those issues, fixing it using technology and believing that you have such fixes available is actually an illusion. All right, so let's talk about science and technology. So there's this common belief that scientific discoveries cause technological advance. Okay, and technology is an applied science. This is actually a half truth. The interaction between science and technology is not as straightforward as we think. This commonly accepted relationship between science and technology advance may actually be inverted as technological advances propel advances in science. Because I'll discuss this in briefly how that happens. All right. Okay. So going from science to technology, you have many examples. For instance, you have modern medicine. It has come from fundamental discoveries in biology. Uh, if quantum mechanics hadn't happened in beginning of 20th century, we wouldn't have the transistor, the solid state physics that is the basis of transistor. It is based on quantum mechanics. Likewise, polymer chemistry, scientific ideas in polymer chemistry has given rise to synthetic materials that we all use. What about the inverted relationship, technology to science? Now, frequently, technology has made better instruments that have profoundly affected scientific theories. So, for instance, if Galileo did not have that telescope, okay, however primitive it may appear today, he would not have made the astronomical measurements that confirmed, the the heliocentric model of planetary motion that eventually, established the Copernican model. Okay. Likewise, Pastu, Lister, and Koch. I mean, these are bacteriologists. What Pastu did. He's the Today everybody is talking about vaccine for COVID-19, but the whole idea of vaccine was popularized by Pastu. Then likewise, Lister, I think, was a bacteriologist, and similarly Koch. Now, these people were not really working on understanding of uh, science of bacteriology. In fact, it was at that time, 100 years ago, it was very poorly understood. They were actually trying to develop technology to solve medical problems. And this eventually gave rise to advances in biology and chemistry. Okay. So, in other words, these people all they discovered new methods that challenge scientists for new theories to explain what happened. It is like once human being found out that there is fire, then somebody started thinking about why there is fire, right? And then the science of fire started happening. Okay, so this is one way to look at it, that technology also generates science. And of course, today with computer science, with computer technology, uh, science has fundamentally changed, and I'll come to that in a minute. Okay, so there's an interesting idea about the relationship between science and technology. There's this guy called Melvin Kranzberg, and he says that if you look at history of science, you will find that science and technology have had long indifferent courtship. They've grown up independently. Okay, so in other words, science has not depended on technological advancements, and likewise, the technological advancement has not depended on science. They have been oblivious to each other's existence or taking scornful note of others' presence. Each reaches its puberty, science when scientific revolutions happen, and technology when industrial revolutions happen. And then mild flirtation ensued. In other words, the relationship between science and technology became stronger after the industrial revolution in Europe. Before that, it was happening independently. All right. And so it was a marriage of convenience and necessity, certainly no love match. Okay, right? So people who were more inclined to solve scientific puzzles, they didn't care about what implication it has for humanity. Whereas people who were more inclined towards technological development obviously did it keeping in mind, remember, the organization, how it can develop into an organized application of technology. Okay. And well, military needs help to bring about daring and secret meetings. So often, both scientists and technologists are put together, engineers are put together because of military or corporate needs. So, for instance, the development of the nuclear bomb, which is called the Manhattan Project, it happened in a place called Los Alamos in USA, and it brought the best scientists, American scientists, and the best engineers together. Okay, so there was a scientist head and there was a military head of the project. Obviously, they didn't get along very well with each other. In fact, the scientist head, Robert Oppenheimer, was a very romantic kind of person. As a graduate student, that is when he was doing PhD, he had gone to Germany, fallen in love with a German woman. He used to read Indian philosophy and used to write poetry. So when the first explosion happened, he actually read out a shloka from Gita, where Krishna is telling Arjun that I am the protector and the destroyer of the world. Okay, my radiance is brighter than thousand suns. Anyway, so it's interesting. So that man was later on accused of being a communist spy. He was actually arrested, I believe put in prison for some time, eventually exonerated. So Robert Oppenheimer, very well known for his many works in 20th century physics, including something called Born-Oppenheimer approximation. Anyway, so there's a shotgun wedding. Okay, so they're forced into marriage with each other. That is, science and technology are brought together. So the couple has not lived happily ever after. Each partner retained a good deal of independence. Okay, so science wants to develop independent of technology. In fact, I remember when I started my PhD, I first joined an experimental group, and the supervisor, he was very fond of doing things by hand, and he did not like buying expensive machines. So it was very interesting to work in that lab for a year because I learned a lot of techniques, doing things by my own hands. Whereas other, big groups, they were buying new machines, and etc. So anyway, so lately both have been having identity problems. That is, it has become more difficult to decide who is a scientist and who is an engineer, because scientists are using machines these days, and engineers have to learn fundamental science to understand how to advance technology. So there's constant bickering about who is contributing more to marriage. They quarrel, and divorce is frequently discussed, and it is invariably rejected because they know they both need each other. So that's a very interesting way of looking at the relationship between science and technology. Anyway, remember Thomas Kuhn? I told you that Kuhn looked at history of science. So there's a very interesting observation he made, and that was technology flourished in societies where science remained underdeveloped. Underdeveloped. There's an R missing here. Underdeveloped, and vice versa. And a good example is the Romans and the Greek. The Greeks were very good in things like arithmetic, geometry, philosophical thinking on science, but there's not much known about Greek technology. Whereas the Romans, they made huge aqueducts, okay, water tanks, and big cathedrals. And but the Roman way of counting was enormously complicated. They didn't even know decimals and all that, right? So yeah, so Romans had more advanced technology. Greeks had more advanced science or theory, right? Similarly, in more recent times, France and England had, the steam engine, the etc. France had people like Pascal and people who were, more advanced in the mathematical modeling of scientific phenomena and etc. Um, India had a very bizarre situation since time immemorial. There was a lot of advancement in metallurgy, medicine, and things like that. But theoretical thinking, like mathematics, was confined to a certain exclusive group of people. We have had caste divisions for since time immemorial, whereas hands-on work like metallurgy or medicine, this was the work of the lesser castes. Okay, so there was not much of a communication between these two distinct groups. And as a result, we have lost knowledge of many different things that happened here. For instance, in the Middle Ages, the best steel was apparently produced in Tanjavur in Tamil Nadu, and it went all the way to Syria. And there's this famous Damascus sword, Damascus of Syria, and it was made of Tanjavur steel. It was called Woodsite or something. And then the knowledge just disappeared because it worked within a certain caste group, right? So they would have apprenticeship, and people would learn from their gurus by marks on the wall, or marks made on sand, or etc. And they knew what to mix, how to mix, and etc. And it was only in after the middle of 20th century somebody found out that this variety of steel had some vanadium in it, and that's what made it so special. Okay, but somehow the knowledge was lost through the centuries. So anyway, recently, especially in 20th century, the interaction between science and technology has increased. And even today, a great deal of technological change actually takes place without substantial inputs from science. And the path from science to practical devices takes a long time, and it has its stops and starts and changes of direction. I mean, there is a difference between somebody in the scientific profession and somebody in engineering. So if you are making a bridge, you cannot say in the middle of the project that you don't want to do it because you have another interesting problem in your mind. Whereas in principle, in scientific profession, that can happen. You do not always, uh, are accountable for the grants that you are. I mean, you are accountable in the sense that you have to show that enough work has been done, but you may not necessarily achieve the objectives that you started with because in the meantime, you have been, uh, driven towards other more important objectives that have evolved in the discipline, right? So in 20th century, the most profound flow of information has been from science towards technology. There are several recent theoretical developments like fuzzy logic, adaptive controls that have started showing up in automotive products. And as you know, electric cars are coming with completely new kind of gadgetry, and you don't need 2 centuries lag time anymore. That was common in the past. And theoretical understanding is becoming more and more important in developing automotive technology. So it's become more important for engineers to learn science than ever before. Okay, another reason for the stronger recent interaction is the change made by the computer. So before, science was reductionist. In fact, modern science is the foundations are on reductionist edifice. What does that mean? It's like that classification I showed you. You look at a complex problem like natural phenomenon and break it up into parts. It happens in length scale, it happens in time scale. So for instance, if you are working on understanding nature, starting from all the way from beginning of universe, the Big Bang, to today, you have classifications in time. So the first 3/4 of a second, uh, the weaker interactions, they start giving rise to particles, and then within like 2-3 minutes, the quarks and etc., they start becoming electrons and protons, and then certain million years are spent into forming molecules. And so there are these periods, and there are specialized scientists who work on those specific periods, looking at problems that happened, phenomena that happened in during that period. Similarly, so in other words, reductionism was very important because you cannot study the entire problem at one go. Okay, so you had models, for instance, for climate modeling. You had pressure, temperature, humidity. So there were equations written down. You try to solve, with approximate models. But today, with very fast computers and very large data storage available, you can work on data, for instance, to predict weather. You can work on data for the last 100 years or more for every kilometer. Okay, that what was the temperature in different parts of Hyderabad, what was the pressure in the last 100 years. And then you feed into a numerical model and predict what is likely to happen tomorrow. Okay, so even if there is a lot of lack of predictability, but still it has become much better than before. Weather is far more predictable today than ever before. So with computers, it is possible to divide a practical size object up into minute pieces that science can deal with. A practical object can be analyzed as myriad of small idealized objects, with computer keeping track of books on how these minute objects interact. And this is applied to design of metal parts, computer-assisted engineering, flow of liquids and gases, computational fluid dynamics, that is the climate modeling that I was talking about, and to weather. And biology, computers' ability to predict how large molecules will behave is enabling design of new drugs on faster scale. Okay. Yeah. So the older methods of innovation involve slow accumulation of changes into once the pace of innovation picks up. So it's like, okay, something is not working, try out something else. So this kind of a cut and try is obviously expensive and slow. If if you have a scientific understanding about the problem, obviously it will help you to you know to design a better technology. So this is why the integration of science and technology has become much more today than ever before. Likewise, for instance, when you want to produce a vaccine for COVID, okay, 100 years ago the process would be try out similar uh, you know the bioactive substances that exist, and then keep synthesizing new products and see if one of those works. Okay. So there will be a lot of hit and try and a lot of wastage of chemicals, uh, you know, undesired uh, microbe, uh, microbiological experiments. But with computer modeling, you can eliminate many of these routes and focus on a very select few possibilities, because now you can model every part of the microbe and the chemical that you are going to use, or even the genomic structure. So you can model everything together, and so you can reduce the number of choices, number of options, and that way uh, time as well as the material and energy, everything is saved. Okay. So for cost effective innovation, science and technology are they must integrate with each other in a better way. Of course, you have many 20th century examples of technologies that were predicted in advance from scientific theory. So DNA engineering, obviously, once the crystal structure was scientifically understood and verified, it became possible. Radio, well, I mean, the science was, of course, done for a different reason, to understand molecular structure and etc. And technologically, it was used in communication of radio waves. And then, of course, whatever followed is history. Similarly, television, okay, again, transmission of uh, very low frequency radio waves. Atomic energy, nobody really knew that understanding the structure of matter and structure of atom 100 years ago, nobody would have known that it would someday give rise to electricity from atomic energy, and of course the unfortunate explosive power of atomic energy. Similarly, lasers. The initial research in lasers had nothing to do with the applications that we see today, from anywhere from the surgery of eyes to laser assisted tomography and things like that. The initial research was to understand interaction of radiation with matter, and how you can have coherent, more energetic, focused light sources, right? So computer design and many fundamental principles have come from solid state physics and quantum mechanics, so fundamentals of science. The microchip, of course, is a you know uh, very interesting application of many different ideas, which involve the diode physics to etching of a circuit using hydrochloric acid and ferric chloride and things like that. Then designer drugs, understanding the molecule atomic motion in molecules and understanding chemical reactions, and they have given rise to technology of designer drugs. The counter example is that many scientists have often felt that certain technologies would never be possible. So space flight powered by rockets were thought to be impossible, but that is what we have today, right? Yeah. So eventually, when the technology happened, then it was explainable on scientific grounds. And finally, many theories have contributed to spaceflight. On many occasions, development and application of particular technologies have raised questions that at that time science could not answer. So this is again very interesting that technology gives rise to scientific problems which helps in advancement of science. So thinking of technology merely as an application of science is not really true. Okay, so let me summarize once again why I have brought in technology here. Because the knowledge that we acquire using the epistemology of science is heavily assisted by technology today. Okay, if we did not have computers, if we did not have machines, so for instance, the perception that we have, the natural perception, there are only certain frequencies of sound that we can hear, only certain frequencies of light that we can see. Machines have enabled us to see, to go far beyond these limitations of human existence. So we look at molecules, the processes that atoms, molecules, and nuclei undergo far beyond the frequencies that we can see using naked eye. Okay, and if you look at the electromagnetic spectrum, there's only a tiny bit in the electromagnetic spectrum that is visible light, whereas we actually routinely study, uh, nuclear motion, electronic motion, different kinds of nuclear motion, rotation, um, translation, vibration, all kinds of things that we do using electromagnetic radiation. All this has become possible because of technology being accessible. Okay. All right. So let me end the talk by once again going back to, uh, you know, good old Albert Einstein. And one thing that I have learned in a long life is that all our science measured against reality is primitive and childlike, and yet it is the most precious thing we have. Indeed, science is not as simple as simply making observations, do experiments, make predictions, and then finally theorize. It is not as simple as that. It is far more complex than that. The philosophical aspects of science, the debates on these have never ended. There's no last word on it. It goes on, and there are uh, very important social concerns on the social construction of science. So all this will go on. But nonetheless, it remains an episteme, a way of acquiring knowledge that empowers us to approach truth, perhaps much more than any other institution of acquiring knowledge, be it religion, be it tradition, or anything else. So that's it. So I will now hope that you would have some comments and questions. Thank you.
Thank you, Professor Singh, for a lovely talk. And uh, the, it's open for questions now. Any questions from participants?
I hope people are there.
Yeah.
I'm not, I'm
We are
not-
34 people there,
okay.
and we are on live streaming too. But we didn't know we could go live, so we didn't advertise it much. From tomorrow we would have it, and these lectures will be on the uh, would be there on the YouTube, and I'm
Okay.
sure people will be watching it even later. So here's a question for you,
Okay.
Priya,
Why
Dr.
do,
Priya Sanas. Why do you?
okay.
Yeah, you can read it. Please read.
Yeah, certainly. It's a excellent question. No, there are different ways of looking at it. I mean, we are living in times where it does seem that there is a, rise of certain kind of, political forces that are undermining science. But on the other hand, if you look back and then ask yourself, well, has anything changed in our way of looking at the world? Uh, so, for instance, when there are crises, like for instance the COVID crisis, what do we depend on? I mean, in spite of all the heroic, if you like to say it, gestures of Trump, when it came to crisis in his personal life, he has to rely on modern medicine. So it's not. Uh, I think it's more a political reality than an existential uh, uh, issue. On the other hand, this is also true that the helplessness that modern technology has caused, and this simplistic notion that technology is after all nothing but a application of science, which is, as I explained in fair detail, is not really true. But unfortunately that is a simplistic notion that most people carry, and so that has created a helplessness in people's mind, and I think it is also a reaction to that. And my hope is that it is not going to last for too long, and people are going to realize that it is possible to live with different kinds of belief systems, and yet realize that science as a way of acquiring knowledge is a necessity. Is it the means, the structures of logical reasoning that science provides uh, are different. I deliberately, I do not want to use the word superior or inferior or anything like that. Are different from other ways of acquiring knowledge, and that we ought to take serious interest in science. Unfortunately, in countries like India, the community awareness on science is very poor because the scientific community is also very exclusive. Most of us involved in the profession of science actually have less to do with the idea of science, and it is more a career. Uh, Whereas in Western countries, it is a career for a scientist, but at the same time, there's a lot of community involvement. There are community lectures given by people. Uh, the way science is cultivated right from the early stage of childhood is certainly much better than what we see in our societies. But the hope, I think, in India is that there are tens of thousands, lakhs of young people working in several voluntary sector organizations, in groups of efforts to enhance scientific awareness. There is also a countrywide people's science movement. From the nationalist struggle days, there were science clubs all over the country. The only difference now is that at that time there was a far greater emphasis on a certain kind of rationality. Now I think we have become more sensitive to the fact that there are social processes that we need to understand, and so that is the major difference. Otherwise there is a large scale nationwide people science movement that there are phases. Sometimes it evolves in a very as a strong force, sometimes not. Yeah. What do you think? Why do you think are some? What do you think are some of the unsolved mysteries in science? Where do we stand as on today in solving? Well, it's difficult to say where do we stand. For instance, the mystery of dark matter in theoretical physics remains a mystery. Okay, that is there. Uh, Quantum computing is still on the way. A new kind of physics based computers. Hopefully, in my lifetime, we will see more practical appearances of quantum computing, and so those are major things that are going to happen. Then artificial intelligence integrated with living systems, that is, there are serious ethical issues there, but these are the frontiers of science today. Yeah. Okay.
Yeah,
Thank you all.
lot of
um,
comments, lot of praise for
right. Yeah, I'm
enlightening
glad
others.
you
Good job.
liked it.
And
Yeah, happy World Teachers Day to everyone. Yeah.
science should be done in an open environment, right?
Absolutely. That was not
But
only the
un-
Mertonian prescription. Yeah.
yeah,
Mm.
but unfortunately, there are lobbies in science too,
Mm.
and the scientific community which you spoke about, which which accepts a theory to be true or false, they themselves are being controlled.
Mm, mm.
What do you say? Who controls them? Is it the industry which controls, or institutions, institutes? Which are these communities which control, which
Well,
decide?
see, unfortunately, it is basically a political issue, right? I mean, there are political formations in different parts of the world that want to retain control over people. So, science becomes subservient to such interest. But, I mean, we have come to a point where the planetary existence is in a crisis. We know that there are many things which have cross the boundaries of reversibility. Normally people think of ozone hole and global warming, etc., but there is much more than that. For instance, the nitrogen content in the soil, the phosphorus content, the biodiversity, potable water. There are many such issues where we may not be able to reverse the situation to what was there 100 years ago. So there is a serious crisis that the entire planet is facing. And sooner or later, people in the entire world have to come to know this. But unfortunately, right now, the deprivation and marginalization levels are so high in most of the world that most people are somehow surviving. So these questions are not questions of high priority in most people's minds. And then there is this issue of when there is marginalization and only a small section of society is given privilege to be in the scientific profession, then obviously such a section is interested in continuing their privilege, and they're not really interested in science per se. They're interested more in the career and the privileges that come with it. So that is another reason why it becomes it does not pervade, it does not go to the bulk of the society. So but one has to keep hope alive. Yeah. Is there any connection, parallels between astrology and science? No, there is no connection between astrology and science. If you practice astrology, that is good for you. Go ahead and do it, but it is not science. And the one word of caution, just like to a scientist, we would say that be careful, don't do anything wrong that will hurt you or hurt others. Similarly, if you are doing astrology, be careful, don't hurt anybody, don't hurt yourself either by believing in it too much. No, there is no connection between astrology and science. Astronomy is science. Astrology is not science. Yeah. See,
So,
when we say science, we usually mean modern science. The characteristics that I mentioned have become more and more clear in recent centuries. The science in ancient times, see, that is why things often become confusing. Science in ancient times was often, it was integrated together with other things like religion and other traditional practices. So for instance, even something like if you look at the medical writings from Charak Samhita or something like that, you would find praise of some god or something right in the beginning, some vandana or some stuti, or similarly in all cultures you will find that, right? So because of that, there is a lot of confusion. It is only in recent times that the separation has become more clear. That does not mean that an individual in their lives uh, they live completely a scientist's identity or some other identity. We have mixed identities in individual lives. Okay, that is all right, but we need to understand which part of it is science and which part of it is not science, and we need to understand how by not demarcating the two, we can actually hurt ourselves and hurt others. That is the important thing.
magicians are using science or pseudoscience? Dr. Nessie
Oh,
asks.
yeah, yeah. Well, a magician may be using science to fool you. That is a different thing. I mean, they may do some chemical reactions or something and create, you know, uh, fumes or things like that. That is to, create an illusion. Okay, that can happen. But otherwise, if you start believing that math, what is magically shown, like for instance, a flower becomes a pigeon, or or they use a saw to cut out a human being, and then later on the human being comes back on the stage. Now that is not science, obviously. No good magician will tell you that is science. They will tell you that they have played a trick on you. Okay, I guess so. That's the end of the session. What is the scientific basis of hypnotism? Um, See, these are areas which are gray areas. So one of the first theories that Karl Popper attacked was Freud's psychoanalysis. And because see, Karl Popper said that you need to be able to falsify theories. So what happens is you do a psychoanalysis, and if things don't work out according to your interpretation, then you come up with another interpretation for whatever you witness. So Popper said that Freud's theory is not scientific. Now hypnotism, uh, I have no idea because I have never experienced hypnotism, and I do not think there is any science behind it. It is, it is basically taking advantage of somebody in a crisis, and an experienced, you know, uh, practitioner of mental health can take advantage of that. And when a mental health patient goes to a psychologist, clinical psychologist, one of the first things that happens is the clinical psychologist tries to establish a trust based relationship with the patient. And as a result, the patient then relies and trusts only that clinical psychologist. So hypnotism is just an extension of this. It is the health practitioner taking advantage of this relationship with the patient and making them say things or recollect things which they would normally not do. Okay, so I don't think there is any more than that in it. It is not really a control over the neurological processes in the brain. No, that's not it. What is exactly the human science and natural science? Okay, so I did talk about that a little bit. I did mention that in natural science, the focus is entirely on nature and natural phenomena, whereas in human sciences, human being is at the center of all observations and all analysis. And so self-consciousness of the human being and the prejudices and the biases, the preferences of the human observer are far more prominent in human sciences than in natural sciences. Not only that, in human sciences, there is it is difficult to draw a boundary between the larger humanities and the human sciences. So, for instance, literature, poetry, art, etc. There is no clear boundary between where some things like economics maybe, and um, you can talk about economics as a more like natural sciences, though it is actually not about natural phenomena, it's about man-made phenomena. But something like sociology, for instance, you can have a sociology of literature, sociology of art, right? And so their ambiguity or multiple meanings are sometimes a resource, whereas in natural sciences, ambiguities are not, they don't have much of a place. You have very technical language of mathematics. Okay, right? All right. Yeah. Okay. So what is it? Necromancy and science. Are there any? Again, you know, I'm not really competent to answer this question, but I believe there isn't really. Necromancy has no connection with science. Yeah.
So thanks a lot, Professor Singh, for a lovely
Okay. Thank you so much for
talk.
this
Yeah,
opportunity. Yeah.
and uh, thanks a lot.
All right.
If it's fine to share your presentation
Yeah, absolutely. Yeah.
with
No
people,
problem.
then I will do that.
Yeah. Yeah. Absolutely. Okay. Thank you.
Thank you.
Okay.
So for the participants, please come tomorrow at 10. Join in a bit earlier, 5 to 10, and 10 sharp we'll start the session. I hope you enjoyed today's lectures. Goodbye and
Okay.
thank you.
Bye bye from me. Okay.
Bye-bye.
Yeah.
Thank you.